or move at a constant velocity unless acted upon by an external force. A body will continue in its state of rest. This is when the body is stationary. Or move at a constant velocity unless acted upon by an external force. This is Newton's first law of motion. In other words, a change in the velocity of the... Hello?
Please, can you repeat it again?
Okay. A body would continue in a state of rest. A body will continue in a state of rest or move at a constant velocity unless acted upon by an external force. Okay. In other words, a change in the velocity of a body is caused by a force. In other words, a change in the velocity of a body is caused by a force. Is caused by a force. This is Newton's first law of motion. A body will change in its state of rest or move at a constant velocity unless acted upon by an external force. In other words, a change in the velocity of a body is caused by a force. So what the law is basically saying is that if there is no force acting on a body, two things can happen. One, either the body will be at rest or the body will move at a constant velocity. Let me add this bit of information. When the external force or when the force acting on a body, whether at rest or in motion, acting on a body, whether stationary or moving. So whether the body is stationary or it is moving, and the force acting on the body is zero. Is zero. The body is said to be in equilibrium. The body is said to be in equilibrium. So in physics, when we talk about equilibrium state, then we are talking about a state where the net force or the total force acting on a body is equal to zero. So equilibrium state in physics. I'm stressing in physics because we have equilibrium in chemistry. We also have equilibrium in economics. So in physics, equilibrium state is the state where the total forces acting on a body in all directions on a body in all directions is zero. Is zero. Under this kind of equilibrium, we have two main types of equilibrium. Under this very one, we have what we call static equilibrium, and dynamic equilibrium. We can also, under moment, we can also talk about other types of equilibrium, but under motion, Newton's laws of motion, we have what we call static equilibrium and dynamic equilibrium. In static equilibrium, the body is stationary, or the body is at rest, and the net force acting on the body from all directions is zero. So under static equilibrium, body is at rest. Body is at rest, and the net force and the forces acting on the body in all directions is equal to zero. And the forces, or let me use the adjective, and the net force acting on a body in all directions is equal to zero. Then in dynamic equilibrium, the body is in motion. In dynamic equilibrium, we have a body in motion, or we have a moving body, and the total forces or the net force acting on the body in all directions. Fatima, please mute yourself. So here the body is in motion, and the total or the resultant force acting on the body is equal to zero, and the body therefore moves at a constant velocity. So in dynamic equilibrium, total forces in all directions is zero, and body moves at a constant velocity. So Newton's first law of motion actually talks about these two kind of equilibrium situations: static equilibrium and dynamic equilibrium, where when a body is stationary, it will continue to be stationary, and when it is moving, it will also continue to move with a constant velocity unless it is acted upon by an external force. Okay. Imelda. Oh, she's not here. Okay. Then Newton's second law of motion. Newton's second law of motion. Now, from Newton's first law, when an external force is applied, what happens? Class. When an external force is applied, what happens? Anybody? When a force acts on a body, what happens? Yes, Elikem.
So please, you can cause a change in speed or direction of the body.
And so technically, you have been a disciple of physics for some time. If there is a change in speed and direction of a body, technically, how would you describe that? Elikem, listen. Hey, Elikem. You say when an external force is applied, there will be a change in speed or direction of a body. Agreed. Absolutely. Now, when this happens, technically, how would you term it? Yes, anybody apart from Elikem?
Acceleration.
The body would accelerate. So, when an external or a force acts on a body, or there's an external force, the body accelerates. Okay. So, the second law seeks to quantify or value the acceleration which is caused by an external force. Okay, so Newton's second law of motion can be termed in two different ways. The acceleration of a body is directly proportional to the external force or the applied force. Meaning, when the external force or the force acting on the body increases, acceleration can also increase. Okay, so the acceleration of a body is directly proportional to the applied force and the mass of, let's not use directly proportional. So let's use the acceleration of a body. Okay, let's not use directly rather, but I think proportional rather would do. Once you are bringing in mass, you understand why I'm making these changes later. So the acceleration of a body is proportional to the applied force or the external force and the mass of the body. Okay, so a typical application or to understand this relationship is that, you see, when a car breaks down on the road and there is a need for it to be pushed from the road, if you bring in Anita alone, Anita can only shake the car. Anita will exert a force. And when she does so, she can only shake the car. But shaking the car means that, yes, there is a bit of change in the velocity of the body, because before it was just stationary. Then when she applied the external force, the car could shake but cannot move. Then when we bring in Elikem, Gideon, okay, Nana Kumi, Ella, the car can then move. So you realize that the applied force by you people is what is causing the change in the speed of the car. And so the acceleration, the change in the speed with time, which we are terming as acceleration, is directly proportional to the applied force, but this is also inversely proportional to the mass of the body, meaning that when the force increases, applied force increases, the body's acceleration would also increase. But when the mass of the body increases, the acceleration of the body would also decrease. So Anita, Ella, Nana Kumi, Gideon can push a saloon car. Okay, when you exert a force on the saloon car, you can change the velocity of the saloon car. But the same number of people, if I ask you to go and push articulator, who born dog? Okay, this time the articulator will not even mind. You can't even shake it. What is changing here? We have the same applied force, the same people, but there is no change in the acceleration that much, because this time the mass of the body increases. So it means that when the mass increases, acceleration would decrease. Okay, when the mass decreases, acceleration would increase, on condition that the applied force is constant. Force must be constant. Daniel, I'm listening.
Sir,
Mhm.
please, if the force is small, will the acceleration be small?
What I'm saying is that, you see, under this condition, when you are looking at the acceleration and the mass, it means that for fair judgment, you must keep the force constant. That is why I cited the example that Ella, Anita, Gideon, about 5 of you, pushing a saloon car and pushing articulator. Hereby maintaining the people, I'm keeping the force constant. Is that okay? So a fair judgment is that the force must be kept constant, so that as we vary the mass, the acceleration can also change. Daniel, are you okay? Daniel is not even around.
Yes, sir.
Okay, so that is it. Is there any other question? So Newton's second law, okay, tells us that the acceleration of a body is proportional to the applied force and the mass of the body. This can also be stated in a different way. The different way of stating this is that the rate of change, Newton's second law also says that the rate, I'm coming in. I want to take attendance quickly. I have a lot of you here and you are quiet. Okay. The rate of change of
Please can
the second law also says that the rate of change of momentum with respect to time, the rate of change of momentum with respect to time is directly proportional to the applied force Mathematically, this second law, this second Newton's law is that we are saying F is directly proportional to the rate of change of momentum, mass times change in velocity divided by time. Okay, the numerator m times v minus u is what we are calling as change in momentum. Momentum is represented by the letter P. I will explain in our next online session. Okay, so the rate of change of momentum with respect to time is directly proportional to the applied force. This is also Newton's second law of motion. Newton's second law of motion is also known as the law of inertia. Yes, next I Mel that I said so. Alekem.
so please can you go back?
Okay. The rate of change of momentum with respect to time is directly proportional to the applied force. So either you state it as the acceleration of a body is proportional to the applied force and the mass of the body, or the rate of change of momentum with respect to time is directly proportional to the applied force. Can I continue?
Yes, please.
Okay. Newton's second law of motion is also known as the law of inertia. Newton's second law. Nana Kwenjua.
So please, I thought that Newton's first law is rather known as the law of inertia.
Don't worry, I will explain. Newton's second law of motion is also known as the law of inertia. Motion is also known as the law of. You see, the first law and then the second law are related, so much related. The first law simply says that a body will be stationary or will be in a constant, will be in motion at a constant velocity unless an external force acts on a body. That's the first law. Then the second law also seeks to investigate when there is an external force or applied force, what happens? Then the body whose initially was stationary would move. The body which was then moving at a constant velocity would increase in its velocity, and so it will accelerate. So the first law, second law, so much related. Is that okay? The second law just seeks to measure the acceleration when the external force is applied. So when there's an applied force, the body will accelerate. How then can we measure the acceleration? So it is from this that we have the relation that the applied force or acceleration is directly proportional to the force and inversely proportional to the mass. A therefore is equal to a constant of proportionality F over M. Okay, if we make F the subject, or if we take the SI unit of A, the basic unit of acceleration, force, and mass, the constant of proportionality K is equal to 1. So that we have F is equal to ME. Just as Newton's second law. Now, inertia, the word inertia means that what inertia is the opposition to a change in the velocity or the speed of a body. Inertia is the opposition to a change in velocity of a body. So when a body has a greater inertia, it means that the body can oppose a change in its velocity the more. Now understand this from this perspective. Consider two different people, a slim one and a fat one. If both of them are standing and you want to cause a change in their speed, when you apply force on a fat person and the same force applied on a slim person, you realize that it will be difficult to change the velocity of the fat person than the slim person, meaning that the fat person can oppose the applied force, which is causing a change in its velocity. So when a body has a greater mass, we say that it has a greater inertia. Are you okay? So Newton's second law of motion is termed as the law of inertia because when a body's inertia increases, when inertia of a body has to do with the mass, when mass increases, acceleration would decrease. When inertia of a body, which is its mass, decreases, acceleration would also increase. So the inertia of a body, which is also the mass of the body, has something to do with acceleration when there is an applied force. Class, are you okay? Nana Kwentua, do you understand?
Yes, please.
So it is because of this connection. When a greater mass, there will be a lesser acceleration, meaning the applied force must be constant. And for a smaller mass, there will be a larger acceleration with the same force. So Newton's second law of motion is also termed as the law of inertia. Newton's second law rather. Let's look at the third law. Newton's third law of motion talks about two pairs of forces. Two pairs of forces which act at the same point. Third law of motion. And the third law of motion says that action and reactional forces, action and reaction are equal and opposite. Action and reaction are equal and opposite. Or for any action or for any action, there is equal and opposite equal and opposite reaction. This is Newton's third law of motion. So you see, as we speak, you are sitting on a chair. You exert your own weight on the chair, and for you to be able to sit and comfortably, okay, and do not fall, the chair must also provide a force which is equal to your weight in the opposite direction. So the two forces will cancel each other out, and the net effect is that it will be zero. So the net forces acting on the body will be zero, and that is when you can comfortably sit on the chair. Without the reactional force, you will just break and fall. So when you sit on a chair and it breaks, it means that the chair is not able to provide the force which will balance your weight. That is why you must fall vertically. Is that okay? So action and reactional forces are equal and opposite. Is there any question? Is there any question? No question. Let's look at applications of the laws. Applications of Newton's laws of motion. The first law is applied when astronauts, okay, are in their space shuttle, in space. I told you that when they are being launched, as they get to space at mid-air or mid-space, astronauts can when they get to space, they can off the engine of the ship, and they can move at that constant velocity, meaning that there's no force acting on them. Okay, they can travel at a constant velocity. They can only on the engine when they want to increase speed or when they want to turn. So astronauts apply this in space during mid-air or mid-space. Then the first law is also applied on when people are playing on ice ground. or icy floor. Okay, when there's a force which triggers motion, the body can retain that constant velocity throughout. So maybe there's a collision. And don't forget, when there's a collision with something, it means there is a force acting on the body, and so it will change its speed. So the first law is actually applied on frictionless surfaces, can only be applied on frictionless surfaces. When there is no friction, a moving body can move at that constant velocity unless it is acted upon by an external force. Okay. Then the second law, Newton's second law of motion, is applied in the design of seat belts, automobile seat belts. Seat belts or car seat belts. The seat belt is for safety purposes. How is it used? You see, if you are in a car and it starts to move, as soon as the driver steps or presses on the accelerator, okay, ignites the engine and then presses on the accelerator, the car begins to move forward. But if you've been observant, you'll be realized that while the car just starts and then begins to move forward, you will be going back, clinging to your seats. Please, have you made that observation before?
Yes, please.
So the car will start moving and you will be leaning against your seats, going back. So the point where the seat exerts a force on you to change your state, then you'll be in tune with the velocity of the car. As the car moves on, and then the driver applies a brake to stop it, okay, the car will be stopping, but you will still be moving forward. That is the reason why in buses there is that receptacle which we can hold, because when the driver suddenly applies the brake to stop, because of action and this the external force applied, you would still be moving forward, even though the car is retarding, stopping, going back, but you will be accelerating, okay? And that is the reason why in a bus, when it is just moving or begins to move, you must hold it. You must hold that thing. And when your body is in tune with the velocity of the car, you can now begin to even walk in a car as if you are walking on the floor. But the problem will come when the driver applies the brake to stop the car and you will be jerking, will be thrown forward. Now, it is of this reason that the seat belt is designed. You see, where the car begins to move forward, you will be going back. And so, in going back, yes, the seat can support you. But when the driver applies the brake, the Bediano brake, the melder, when the driver applies the brake for the car to go back, you will be accelerating forward. That is when the seatbelt pulls you into your seat. Now, it is much of a problem when, unfortunately, during driving, a car behind you hits you from behind. When your car is hit from behind, what will happen is that you will be you see the applied force hits the back of your car, and so the force will push your car forward. So you will stick to your seat, hit your seat. Now, in the event where the driver hits your car in front, what will happen is that the force will be exerted on your car in the backward direction, but you will still be moving forward. Now, you move forward. Your acceleration forward depends on the magnitude of the force, the amount of the force. So when the collision is so much, you will be moving forward with that same force. And look at a car with that weight hitting yours. So if you don't have the seatbelt on, the driver can hit the chest against the steer or the dashboard. Usually, and sometimes, unfortunately, whenever some accident occur on the road and car occupants do not have the seatbelts, they can even go to the extent of being thrown out through the glass. That is why you must have your seatbelt on. Nana Kwame.
Yeah, but isn't that an action reaction force?
Yes, action, but you see, it also has to do with acceleration. You accelerate in the opposite direction, okay, with the actional force on your car. So the actional force will be the force which is exerted on your car, and the reaction is you being thrown out. Okay, so yes, I agree with you. It has something to do with Newton's third law of motion, but we are judging the acceleration of the passenger within the car. So your acceleration is directly proportional to the force applied, but the direction of the force and the acceleration of the passenger are oppositely. That is why you will be thrown forward in the event. Nana Kwame, do you understand?
Yes, sir.
Okay. So the application of the seatbelt is a classical example under Newton's second law of motion. Don't forget, passengers are not allowed to stand in a train or stand on top of a train because of this same thing. In the event where the driver applies the brake, you will be thrown forward. Passengers are also not allowed to stand at the upper deck of this double-decker buses, because when there is a brake, you will be thrown out and you can fall heavily and then be injured. Then application of the third law. The third law has a lot of applications. The first one is the launching of rockets. Launching of rockets. You see, there's rockets which are launched to go to space. Okay, rockets are launched and are given a certain velocity known as the escape velocity. So they get off from the effect of gravity on Earth. Now, the force with which the rockets could just move within the atmosphere and then escape the gravity of the Earth has to do with the fuel. So it is actually fuel, and it burns consistently to give it that force. And during burning, the fume, the smoke is made to escape in the downward direction. The thrust or the force and the pressure with which the smoke escape through the nozzle exerts a reversal, that same reversal force on the rocket, and it is this force that is used to actually propel the rocket in that upward direction. So as the smoke and the fume escape with that pressure and force in the downward direction, we have that same thrust or force and pressure acting on the rocket in the upward direction. So that is one application of the third law. Another application of the third law is during swimming. If you are somebody who is a good swimmer, you see, during swimming, you would exert a force on the water in the backward direction with your legs and then with your hands. Okay, so whilst you throw your or shoot your legs and hands in the backward direction, there will be that equal force acting on your body in the forward direction. So action backward, and then you are shot forward by that equal force as well. So it is applied during swimming. The third application is, you see these firecrackers which are launched during Christmas. Some of them are such that it is launched, put at a particular position, then the matchstick is ignited and then connected to the cracker. It burns, produces smoke, and when the smoke is enough and escapes, okay, through the receptacle, similar to how the rocket also works. So the escaping smoke, propels the firecracker in the upward direction, and it is thrown, okay, into the atmosphere. So the working of the firecracker is also similar to that of the rockets, also an application of it. And you can also demonstrate the same thing. Inflate a balloon, then let the gas within escape, okay, through the outlet. You realize that the balloon would also be, going forward in the air in the opposite direction. So these are some of the applications of Newton's third law of motion. Please, is there any question? If you have any question, quickly ask. All right. Emelda. Anita.
Yes,
Any question?
no, please.
Osafo.
Okay.
Any question? So this is the nitty-gritties of Newton's laws of motion. Today being the last day of our meeting, honestly, the next thing is to figure out how to apply, especially the second law in calculations. But I'm going to leave that for next July. Hello. Hello. Okay, so can you hear me? Class, can you hear me? Hello.